Good morning. Good morning. Shall I start? Shall I start?
Yes, sir.
We have discussed the sign convention. Next, we'll derive the relation between loads, shear force, and bending moment. Relation between load, shear force, and bending moment. Let us consider a cantilever beam of length L subjected to uniformly distributed load. I'll take a small section dx for my study, or delta x we call my study. This is of length L subjected to UDL W kilonewton per meter. I can say small length delta x for study. If I exaggerate this and write, this would look like this: W kilonewton per meter. This is length delta x. When I take the suction, if I take the suction like this, there will be a shear force. This shear force I will take according to my convention. I will consider positive shear force like this. Left hand side, it is from the suction. If I assume suction here, it is acting upwards, and towards right hand side, this is positive shear force convention. Positive shear force. So this is causing on this side for the positive shear force. This should be smiley face. This should be moment. This is shear force F. This is momentum. On this face, this is there is a small variation in shear force. When you turn from this edge to this edge, the shear force changes by small magnitude. I will indicate it by F plus delta F. And the bending moment changes by small magnitude. I will indicate it by M plus delta M. Okay. Throughout the length, shear force and bending moment are changing. And I will indicate that small change in magnitude of the bending moment and shear force by delta F and delta M respectively. Okay, where F is the shear force, M is the bending moment, F plus delta F is a small change in shear force, M plus delta M is a small change in change in bending moment. The small change is delta F and delta M. Okay. Now for equilibrium, summation of forces should be equal to zero and summation of moment should be equal to zero. I will consider my for moment. I take this point O. This is my point O. Okay. The summation of forces is equal to 0. In this case, summation of force is only in y direction is equal to 0. I can write F minus F plus delta F. This load W, the magnitude of this load is W into delta X acting downwards, minus W into delta X is equal to 0, or delta F is equal to minus W delta X. Minus delta F is equal to minus W delta X, or minus this delta f is equal to minus w delta x. Okay, use it like this. Minus delta f minus w delta x is equal to 0, or delta f is equal to minus w delta x. Okay, now I can write this as delta f by delta x is equal to minus w. We know that according to mathematics, when we are read in limits and the continuity, that as delta x limit delta x tends to 0, this delta f by delta x will become equal to df by dx, which is equal to minus w. So it indicates that for as the this length tends to 0, that this indicates the rate of change of, it means to say that rate of change of shear force is equal to magnitude of load, that is magnitude of load, or you can say that slope of shear force diagram is equal to magnitude of load. We will discuss this. Slope of shear force diagram is equal to magnitude of load. So if I consider the slope of shear force diagram, I'll get some slope of shear force diagram, that df by dx should be equal to w. Okay, that is, you should always remember that I have considered a constant load. Sir, one ನಿಮಿಷ sir. You should always consider that it is a constant load acting at along the length of the beam. Okay. Next, no, the second requirement for equilibrium, summation of moment is equal to 0. I'll go back to this. As I'll assume that clockwise moment is positive. Okay, summation of moment of point 2 I'm considering. Summation of moment. This is anti-clockwise moment. Therefore, minus m, and this is also anti-clockwise. Minus m plus delta m, minus of m plus delta m. This force F into perpendicular distance x is causing a clockwise moment like this. This force into this is causing a clockwise moment. Let me write it as plus F into delta x. This force F plus delta f about the same point was 0. This W into delta x, this is delta x by 2. I have told you entire load will be concentrated to the center. W into delta x, this is delta x by 2 from this point. W into delta x by 2, it's causing anti-clockwise moment, isn't it? Anti-clockwise moment. Let me write, it's equal to magnitude of load is W into delta x into delta x by 2 is equal to 0. Since delta x is itself small, delta x square by 2 is negligible. Negligible. This term is negligible. With a small quantity, we can neglect it. And this reduces to minus delta m plus f into delta x is equal to 0, or delta m is equal to f into delta x, or delta m by delta x is equal to 0. Limit delta x tending to 0, delta m by delta x, which is equal to dm by dx is equal to f, which means to say that dm by dx is equal to f, which means to say that rate of change of bending moment is equal to magnitude of, I will discuss this one first, magnitude of shear force, shear force, or slope of rate of change in the sense is on the same, slope of bending moment diagram is equal to the shear force at that point. Now we should discuss related to this. Is very important for our study. Make serial number, load, shear force, load, shear force, bending moment. Okay. Serial number one. When load is zero, load is zero. That is, for example, let us consider simple supported beam. Load is zero. There is no load here. So we know that df by dx is equal to minus w. Since load is zero, which is equal to zero, this is equal to w, this is equal to zero. If I want a magnitude of f, I should integrate that. Therefore, integration of df by dx is equal to minus w, which should be equal to, sorry, which is equal to integration of 0, or f is equal to, what? 0, integration of 0 is constant. When there is no load, shear force is constant. When there is no load, shear force is constant, like this. In this case, if I take a shear force diagram, shear force will be constant like this. This is A, this is B, and this shear force is constant like this. Okay. Give me a moment. Okay. Now, when for that, when there is no load, this is A, B. When there is no load, shear force is constant, and the bending moment, we know that dm by dx is equal to f. In this case, dm by dx, shear force we got it as constant. If I want the bending moment, I need to integrate it, or m is equal to c into x. If shear force, if there is no load, shear force is constant. When there is no load, shear force is constant, and bending moment, is linear. The bending moment curve will be linear like this. This is A, B. It can be like this, or I'm giving just, there are four possibilities. I'm giving only the positive, only two possibilities. We'll discuss all the possibilities like this. It is linear. I'm indicating this as linear. This bending moment will be linear. Bending moment is linear. Bending moment is linear. Okay. Second case. Second case. When the load is constant, load is constant, A, B, constant in the sense it is UDL. They will represent either like this or like this. You should not be confused like this. When the load is constant, we know that df by dx is equal to minus w kilonewton per meter. That is integration of this will become f is equal to minus wx. When the load is constant, shear force is linear. Always, when compared to load, shear force is 1 degree higher, and bending moment is one more degree higher. Okay. Therefore, this shear force would be point A, point B, like this. And there are four possibilities. I'm just giving two possibilities like this. Okay. Now bending moment dm by dx is equal to f, or if I want m, I need to integrate this. Or bending moment is, instead of this, shall I write integration of minus wx, forget about sign, or m is equal to wx square by 2. If you want c, you can add it, wx square by 2 plus c. Therefore, bending moment and shear force is linear. Bending moment is quadratic, or we call it as parabolic. Parabolic. So bending moment can be like this, or like this, or like this. There are four possibilities. Okay, this is bend. You should remember. I am giving just this shear force is linear. Bending moment is quadratic or parabolic. This is x square term. This is the x term here. The linear or quadratic in this case. Next. Next. When the load, we discussed load was constant, load was zero, load was constant, and load is linear, as in case of UDL. Load is UDL, linear. The load is linear. Shear force would be df by dx is equal to minus w. This is, they will give the magnitude of this load, w kilonewton per meter. This is linear. Load itself is linear. Df by dx is equal to minus w into x. Whereas in the previous case, the load was constant, it was equal to w. Therefore, for shear force, I need to integrate to get w, sorry, f. Therefore, the f is equal to minus w into x square by 2 plus c. Therefore, when the load is linear, shear force is 1 degree higher, quadratic. We need this curve. How the shape of the curve, not to plot shape of some bending moment diagram. We need this curves, whether it's linear, quadratic, or constant. We require this. And dm by dx, which is equal to f, which is equal to minus wx square by 2 plus c, or m is equal to minus wx cube by 6 plus c1x plus c2, whatever. So when the bending shear force is quadratic, bending moment, there is a cubic term here. Bending moment is cubic. That you should understand. Okay. Keeping this, you should keep always in your mind. Okay. Always when there is no load, as in this case, zero load, the shear force is constant, whereas bending moment is linear, like x term straight line, that is y is equal to mx plus c. And then when shear load is constant, shear force, when load is constant, shear force is linear, like the straight line, y is equal to mx plus c. When shear force is linear, bending moment is quadratic like this, a curve like this, x square, a parabol curve. Okay. When the load is linear, shear force is quadratic, same curve like this or like this, quadratic curves. And the bending moment is cubic, that is third cubic order curve like this. Okay. Next, see, we have established a relation. Now we know that dm by dx is equal to f. So, in case if dm by dx, there is a slope of shear force diagram is equal to 0, then 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 bending moment bending moment can be maximum or minimum, isn't it? If the first derivative is 0, then second derivative can be negative or positive. We don't know. We say that generally we say that it is maximum as we are required. If the slope of the shear force diagram is 0, then the bending moment can be maximum or minimum. While solving the problem, we require that whenever our, for example, slope of the shear force diagram in the sense that is before that, for example, this is the bending moment diagram. At this point the slope is 0. There is time when you draw a tangent, the slope is 0. The slope of shear force diagram is 0. Bending moment is maximum or minimum. The other way could be when when shear force is 0, bending moment is maximum. For example, when you plot a shear force diagram A, B, C, you will get assume that shear force will be getting like this. This point where shear force is 0, this is the point where bending moment is maximum. If I consider like this, if you consider like this, A, B, C. This is the point where bending moment is maximum. The point where the shear force is zero. This is shear force diagram. This is bending moment diagram. The point where shear force is zero, bending moment will be zero maximum. Or in other words, the slope of bending moment diagram is equal to zero. There is no slope here. This straight line. So slope is zero. In other words, we will go in the other way. Wherever the shear force is zero, we will find the distance and we'll find the point where the bending moment is maximum. Okay, keeping this in mind, I need to give few more points. So we discussed shear force and bending moment. So what is shear force diagram and bending moment diagram? Shear force diagram, the variation of shear force along the length of the beam is called as shear force diagram. The plot of variation of shear force diagram along the length of the beam is called as shear force diagram. Similarly, bending moment diagram, bending moment diagram, the plot of variation of bending moment along the length of the beam, or the bending moment is varying throughout the length of the beam, is called as bending moment diagram. Okay, there's one more concept. This is called as point of contracture or point of, is also called as point of inflection. For example, if we consider a bending moment diagram like this, so assume it is like this and it is going like this. This is A, B, C. Okay, 3 points. This is the point we are talking about. The point where bending moment is 0 or changes its, this is positive up to point B and negative from point B to point C, and 0 at this point. This is called as point of conflection or point of contracture. point of contraflexion. The point where bending moment is zero, in this point is zero, or how we can determine it is, it changes from positive to negative. Bending moment diagram changes from positive to negative. The point where bending moment is zero changes, its sign is called as point of contraflexion. Why it is required in the sense, if the beam, if the this is the beam which was bending like positive bending moment in the sense it is positive for me like this. It was bending like positive. Now beyond this point, the beam tends to this is negative for convention. The beam which was bending like this beyond this point tends to bend like this. That's why this point is significant. Okay, why we will require shear force and bending moment diagram is the regions where the shear force is maximum. Those are the regions where the shear stresses are maximum. The regions where the bending moment is maximum. Those are the regions where the bending moment is bending stresses are maximum. To know the bending stresses and shear forces, we require the shear force and bending moment diagram. Okay. Now, now let me give the variations. This is what I'm talking is shear force. Uh, Take the three cases. Shear force is positive constant. The shear, this is I'm coming from left to right. Assume that this is C and I'm taking points in. You can take the E and B also, but I'm taking C and D. C and D. Shear force is constant. Out with the bending moment. Any curve, any curve, the positive slope in the sense, positive slope means curve pointing upwards, or a curve moving towards upwards is the positive slope. Okay, now for this, positive slope would be like this. Positive slope would be like this is shear force, this is bending moment, positive constant. Shear force is constant, bending moment will be linear. This is bending moment linear since this is a positive slope. So a positive slope means the curve has to move towards upwards from point C to D. This is linear. Next, shear force. Shear force is linear, linear like this. C D, C D. Okay, and bending moment. When you see what I have told you, you should always remember this. Slope of shear force diagram is equal to magnitude of load. Now, the curve will be something like this. Why? Because you should remember that slope of shear force diagram, under 10 minutes remaining, I'll complete only this. Slope of shear force diagram is equal to magnitude of load. This is the magnitude, this magnitude is lesser here, this magnitude is higher here. If you take the slope here, if you take the slope here, this slope, assume that the slope is something like this slope is something like this slope is like this, but as you go here the slope increases. It means to say that my curve, that the slope also increases. Slope is equal to magnitude of the load. There is more slope here and there is lesser slope here, therefore the curve has to be like this. Okay, I think you should look after this. I'm giving the idea, you should also work on this. Now, when when the slope of when the shear force diagram is linear like this, the shear force is like this. Positive slope in the sense the curve. This is also positive linear, positive linear, positive linear. It means that this says that slope becomes more positive. Positive linear. In this case, this is slope. It moves upwards. But you can see that the slope in this region is this much. This always already reduces. This reduces. Is it audible? Is it audible? Hello?
Yes, sir.
Okay. Now, see, the slope is reducing now. If I take the slope like this, slope is reducing. At this point, the slope almost reduced. The curve has to be like this for this. When the shape of diagram is like this, the curve has to be like this. Slope becomes less positive. Slope becomes less positive. No, just try if possible. This is spoke about positive, yes, positive shear force diagram. Next shear force, if it is negative like this, I'll take all the four cases. This is positive. The shear force is negative constant. Negative. The slope positive in the sense it is moving upward is positive. Moving downwards, this is point C, point D. Moving downwards like this is negative slope. That you should know. Check it. Check in what is positive slope. Any curve which is moving upwards is said to be positive. In the other sense, when it is moving downwards, it is negative. Okay. Now, if in this case, if the shape for diagram is like this, then negative linear of shear force, negative linear shear force, then your bending moment would be like this. This is moving downwards C to D, and you can see there's a lesser slope. Slope increases because slope is equal to dy by dx. As the magnitude of y increases, this y increases and x reduces, and this slope increases. I want this slope is equal to magnitude of this load. Slope is equal to magnitude of this load. This slope is lesser, this slope is higher. This slope is less, and this slope is higher. Okay, slope is equal to dm by dx is equal to f. Okay, next, the other thing, the other way would be like this. Now I can write the curve always pointing downwards. This is C to D. You can see maximum slope at this point. Slope reduces, and it reduces. So maximum in the sense dm by dx, slope of bending moment diagram is equal to magnitude of shear force. Therefore, magnitude of shear force is higher here. The further it means to say that slope should be higher. This is lesser here. Slope should be less. Okay, these curves are required for us to plot the shear force and bending moment diagram. Have you understood this? This is conceptual. You should understand this. Have you understood this? Have you understood this? Abdul Razak, Dhruti,
Yes, sir.
Mekala,
Yes, sir.
Satish Paul, Ravindra,
Yes, sir.
Rakesh T,
Yes, sir.
Ritesh TR, Sanjay, Sugun. I don't know. Switch on the phone and went off. I think. Okay, I'll be stopping at this point. From next class onwards, we'll solve the problem. Another 8 to 10 classes I may require. I'll complete the problem by December 12 or 13. Okay, I'll stop at this point. Thank you. Any doubts if you have, we can ask me. Any doubts you have?